Yes, in the last class we have gone through some of the concept in theory of elasticity and plasticity. We are discussing regarding the theory of elasticity part only, and in that one also we have discussed regarding definitions of the elasticity and what is the mechanics and what is the machines and what are the type of the how machines has been divided depending on application of the forces, what is the kinematics and what is the kinetics. These all are we have seen, and some of the important concept theories concepts in theory of elasticity also we have seen. Okay, and these three we have seen: external forces which we use to apply over the body, and stresses resisted by the body which called as the internal forces or internal resistances. Okay, and deformations of bodies like strain and displacement relationships are deformation strain relationships we have seen. uh, some of the concept of this theory of elasticity we have seen, and some of the external forces we can see here, and we have gone through this one: body forces and surface forces, and how we used to call as the stress with respect to this body we have seen in last lecture. Okay, and how we used to define the stress, and that one for the particular elemental body we have seen, and what is the normal stress in this case we have seen. Okay, similarly deformations of the body which is produced by the deformations of the bodies also we have discussed, and some of the basic assumptions also we have gone. Okay, some of the notations regarding the forces and notations of the stresses also we have seen in the last lecture. Okay, up to this we have gone for this theory of elasticity. Then after today I am going to discuss regarding the concept of direct stress and shear stress. Okay, how we used to find the direct stress and how we used to find the shear stress over the element. Okay, here we can see concept of direct stress and shear stress. The rectangular component of the force vector, the del F, referred to as the corresponding axis. Del F is the force, okay, which is corresponding to the referred axis. If you take any axis, each axis is having the each force. Okay, del F is nothing but the force, elemental force, which is the force which is taken by that particular element. We used to represent with the del F. Okay, for suppose the force which is applied over this body, which indicates in the direction of F, we used to, if you are applying the force in the direction of F, okay, for that particular element is going to take the force del fx. Okay, small amount of the force, that small element will take small amount of the force from all those total force. Okay, from that resulting force, del fx in x direction, del fy in y direction, and del fz in z direction. You can see all these three forces, whereas the del ax is nothing but area of cross section of this particular element, and whereas this cross section is having the dimensions, del y is the depth and del z is the length of this particular element. Okay, the smaller element will have the smaller dimensions, and these smaller dimensions of this particular surface or area will take smaller amount of the forces, and these forces we used to give the stresses. If you see here, del fx by del ax, the force in that particular direction, and this one is indicates the stress in the normal direction. Now this stress is normal to the surface of that particular element, whereas the del fy by del ax indicates the shear stresses, whereas the area of the element will be in the normal to the x-axis, and force is applied in the y-axis. Okay, force will be acts in the y direction. Okay, stresses will be generated in the direction of y, and similarly stresses will be generated in the direction of z. Force will be give the stress in uh, z direction. Okay, these values of the three intensities are defined as the stress component. These three are indicates the stress component: sigma x, tau xy, and tau xz. You can see here these three are the stress components, and the stress components parallel to the surface are called as the shear components, denoted by tau. The stress component on the x face at a point O are defined as the follow in terms of the force intensity ratios. These are the force intensities ratios with the limit of this one. By limiting this length, we have here boundaries, we have here limits up to certain width and certain depth we have to go. For that one we used to indicate the intensities of the intensity ratios like this we used to do. Okay, as explained earlier itself, sigma x will be indicated, this particular stress will be indicated like this with the with the limits of the cross section. Del fx by del ax for normal stress, tau xy will be limits tends to limits of del ax tends to 0, del fy by del ax, and tau xz will be indicates force in z, x direction will experience to take the shear in z direction, area of the x, normal area of the x takes the force in z direction. Okay. The above stress components are illustrated in the figure. You can see here in this figure will be use the stresses. Okay. These all are regarding stress components. And concept of the direct stress and shear stress we used to utilize like this. And these forces will be, if you see in this direction, shear stress will be parallel to the area of the cross section. Here also we can see area of the cross section, the force of this particular area, force in y direction will be parallel to the area of the x. Okay, in x direction, y directional force will be parallel to the x surface. Okay, x force applied in x direction and which will be parallel to the y direction. Okay. These two are the shear components which are parallel to the cross sectional area, and this one is the normal component which is perpendicular to the cross sectional area. Okay. For suppose we have different type of vectors and scalars, different type of force components, stress components. Okay. Whereas we here if you see any body, for suppose if you take any body here, okay, if you take this body as the material, here what we can say, any point O, if you consider a point O in this body, and I am taking point O be the point in a body shown in figure, and passing through that point infinitely many planes, okay, many be drawn at the resultant forces acting on the face of plane is the same. Okay, if you take a uh, resultant stress will be acting over this particular body. Okay, that will be in this direction, whatever may be the direction. The resultant stress will be acting over that particular plane. Okay, and infinitely many planes may be drawn. If you take wherever plane you require, where area interest of the area you want to take, if you take there, okay, the resultant forces acting on the face of the plane is same. The resultant forces will be same on those planes. If you take force, resultant of the forces will be same on those particular planes. And stresses on the plane, these planes are different because the area and the inclination of these planes are different. Okay, stresses will be different. Forces, resultant forces will be same, but stresses on the particular plane will be different because of, if you cut here in this location, the cross-sectional area will be different. If you cut incline, the cross-sectional area will be like some ellipsoid, okay, elliptical shape of the plane you can see. Okay, like that plane of the area of the cross-section will be changes. If area of the cross-section changes, stress parameters also changes, whereas the force will be same, resultant force will be same in all cases, but area of the cross section will be changed. Because of that reason, stress will be varies. Okay. Therefore, for complete description of the stress, if you want to describe this stress, we have to specify not only the magnitude, direction, and sense. Sense is nothing but here direction of the force, whether it is you are applying negative direction or positive direction. Okay, sense, but also the surface on which it is acts. Okay, here in case of tensor, we used to take surface on which surface it is acting. That one also we used to consider. Okay, when we consider the surface of the force over that surface, that particular stress is called as tensor. Okay, the stress is that particular stress parameters called as the tensor. Okay, in vectors we can see two components like magnitude and the direction. In case of scalar, we can see only magnitude. Okay, we can see the only magnitude. In case of vector, we can see direction as well as magnitude of the body. But in case of tensor, we can see the surface of the body also we used to consider uh, for the calculation of the stresses. Okay. Those type of stresses we used to those type of bodies we used to call as the tensor. Okay. If you see from this figure depicts three orthogonal coordinate planes representing a parallelepiped on which are 9 components of the stresses. You can see here each plane is having the 3 components, but there will be the repetition of the stresses. You can see here xy and yx will be depicts same values, and whereas xz and yz same values, it will reflect same values. Tau xy, tau yx will be reflect same values. Tau xz, tau zx will be reflect same values. Tau zy and tau yz will be reflect same values. If you take all these parameters, 3 faces of the body, top, side faces. These faces indicate the total how many components? 3 normal components and another 6 diagonal upper and lower triangular components. Okay, normal component and surface components of the stresses. Shear stress components, you can see 6 and normal stress component 3. Total how many components will be there? Total overall we have 9 stress components. Okay. Whereas 3 are the direct stress components and 6 are the shear stress components. In tensor notations we can indicate like this. This can be expressed by the tensor tau ij, whereas I is the x, y and z, and j indicates the x, y and z. Okay. In matrix form, this all can be indicated like this: tau xx, tau xy, tau xz, and tau yx, tau yy, tau yz, and similarly tau zx, tau zy, and tau z. These are the stress parameters. In terms of shear stress component, if you want to indicate like this, we can indicate, whereas the tau iz indicates the tensor properties of the material, tensor component of the material, and this one also can be indicated like this: S is equal to, whereas diagonal elements has been taken as the normal stress component, force and plane of the area both will be same direction on the same plane, force has been taken on the same plane, like that we used to take here tau xxy and sigma x, and for the tau yy also same thing, sigma y, tau zz also same thing, sigma z. Whereas these all are the normal stress component, remaining all are the shear stress components. Upper side and lower side of the triangles we used to take same component. These all are indicates the stress components of the body, tensor components of the body. Okay. And similarly we will see type of some, there will be some type, various type of stresses will be there, and we know all those, whereas the stresses may be classified as in 2 ways, that is according to the type of body on which they are acting, or the nature of the stress itself, which direction it is acting. Okay, type of body and as well as nature of the force which is acting. So the stress could be one dimensional. If you see in this direction, in this diagram, we can see the one directional forces. Here we can see only axial forces which can taken by the axial element. Okay, the member which is carrying the only axial forces, like uh, some of the struts or column members where they used to take as the axial forces. In trusses we can see strut will be there, and those strut will be carries only axial forces. Those may be compressive or tensile. Okay, their nature may be compressive or tensile. And some of the body forces, if you see two-dimensional bodies, okay, where we can see this type of two-dimensional bodies. For suppose if you take any retaining walls where they used to resist backside of the forces, okay, which are acting forces from the backside, though they used to create stresses in lateral directions. Okay, their thickness will be very negligible. The bodies which are having the negligible thickness, okay, like retaining walls, or if you take any dams, they used to resist the force, water force from the backside, and stresses will be generated in the lateral directions, in the direction of the x and y. If you apply the force in water force in z direction, the forces stresses will be generated in the x direction and also y direction. Why? Because in the z direction, thickness of that particular dam will be very negligible when comparing with the other two parameters, other two dimensions. Okay. And similarly, some three-dimensional bodies for we used to use for the in case of water bodies. If you apply any water force or any foundations, if you want to generate inside the water bodies, there we used to take for the foundation cases, we used to use solid bodies. Okay, they used to create solid type of stresses. This type of stresses, they used to create stresses in three direction. All three direction we can see stresses. Okay, these are called as the three-dimensional stress components. Okay, all these are related to the type of stresses. Okay, with this I am stopping regarding the different type of stresses and stress component and some of the concept of the stresses and shear stresses. Okay, in the next class we will see the some differential equations regarding the two-dimensional bodies and also three-dimensional bodies. Okay. Thank you.